You got it? All right. I will begin. Dear Father, we thank you for this day again, Lord. I thank you for the students, and we thank you for your many mercies for us each day, Lord. Just help us to glorify you in what we do this day, Lord, and help us to enjoy the weekend, which is about to start. In my prayer, Lord Jesus. Amen. I know you guys you can hardly stay in your seats. All the excitement of the opening ceremonies at the Winter Olympics tonight, it's kind of like, it's just in the air. Everyone's so excited about it. So I understand if you're distracted and it's hard for you to focus on what I'm doing today in class. I mean, I understand. But I should probably show you the proof of the CCP, column correspondence property, right? Which says what? Linear dependence found in A is also found in any row equivalent B. So here I'm assuming that A and B are, of course, matrices of the same size over some field, and that they're row equivalent. Now, what does it mean to say that there's a linear dependence? So let me make this more precise. Theorem. If A is row equivalent to B, let's say row equivalent, what's that mean? That means that there's a finite, sequence of elementary row operations which will take A to B, right? Which pragmatically means we can use elementary matrices to multiply one to get to the other, right? If this, and if we have, the sum of Ci column I of A, I equals 1 to, let's say, n, is equal to 0. Well, I think we could take, I think that's fair enough. We can take any, that's just what I really want. I'll tell you what, let's suppose that column J of A is equal to a linear combination I equals 1 to n of, C, Ci column I of A, right? So this is a linear, I'm writing one column of A as a linear combination of all the columns of A. This says nothing about the matrix. You can do this for any matrix. It's kind of stupid. Just take all of the coefficients to be 0 except for the jth one and set it equal to 1. Column J equals column J. Yay, linear dependence. It's not especially interesting, but it's there. All right. Anyway, so suppose you've got this linear dependence of the columns of A, right? And then, well, guess what? Column J of B is equal to the same linear combination of the columns of B. Same coefficients, same linear dependence. This is the linear correspondence, the column correspondence property. All right? There's a more technical statement of it. Proof. Here's the proof. A row equivalent to B means what? B is equal to EK minus 1, E2, E1, right? Times A. And since it does not give me joy, or especially a lot of insight to write all of these elementary matrices, why don't we just collectively call the product of all these elementary matrices E? Right? So then this is EA. All right? We know we can do this from our discussion of Gaussian elimination and row operations and all that. Suppose that column J of A is equal to the sum, I equals 1 to n, of Ci column I of A. Right? Suppose there's linear dependence. What's my next move? How do I convert this to a linear dependence about B? What do you think I should do? How about this? Multiply on left by E. What's that give me? Well, I guess I should notice that if we look at E times A, that's E times what? Column 1 of A, however many, I guess we're doing n. I'm thinking about A being m by n. It really hasn't come up yet in this proof much, but suppose these are both m by n matrices. That means there is n columns, right? So if we got column 1 to column n, and we left multiply, that's I blame Calculus 3 for that. They got me to stay up late last night creating homeworks for them. Some of you are in their number. So I'm not thinking entirely clearly today, partly because I was up far too late creating silly homework problems for Calculus 3, which I should have just told them, why don't you just look at the examples in class? Come on, people. But that simple phrase did not occur to me, so I invented 3 hours of work for myself because I'm an idiot. Anyway, E times A, column by column, is E times column 1 of A, E times column n of A. Anyway, the point here, guys, is that E times column J of A is actually what? That's actually column J of EA, which, as you have pointed out, is column J of B. Very good. And also, E times the sum, right? Sorry, I'm starting to work where you guys can't see. Oh, let me stop. I should really make myself a note. Do not write anything below this line. You guys should make me write this line at the start of every lecture, because there's some of you who can't see below that line. All right, so if we multiply E times the linear combination, right? Sum I equals 1 to n of Ci column I of A. Well, then by properties of, matrix column multiplication, we can pull the sum out, we can pull the constants out, and we just got E times column I of A, but what was that? We just figured out that this is really what? Nothing more than column I of what? B. So therefore, multiplying the left, column J of A gives me column J of B equal to the sum I equals 1 to n Ci column I of B, which of course is exactly what we set out to prove. Do you guys understand? I mean, I'm sorry, my organization here is not quite optimal in my view. I took this equation star, right? I multiplied star on left by E. this right here is the left-hand side of star E, E star rather. Right. This up here is the right-hand side of E times star. Right. And so here, this is, left-hand side equals the right-hand side of E times star. It gives me this. So what I'm saying is I multiplied an equation by E on both sides. I looked at the left-hand side, simplified it. I looked at the right-hand side, simplified it. If they have to match, then matching, of course, is exactly the thing I want. If I had a board that was about 3 feet longer, I would have just written this on one line and I wouldn't have had this awkward discussion. But I probably shouldn't write here. I can write there once. I choose my words carefully because it'll be there the rest of the semester, or at least until I paint this room, but nobody wants that, right? Let's see here. Any questions? So this is the column correspondence property. So what are the two big concepts that we've talked about? In the video, I asked you to watch, Wednesday, or if you've seen the help session from yesterday. The big ideas are spanning, right? And what's the other big idea? Yeah, linear independence. And the column correspondence property helps me answer questions about both of those. All right? So the most important sort of corollary to the column correspondence property is when we apply this to the matrix in its reduced row echelon form. Because it's very simple to see linear dependence that appear in the reduced row echelon form. For example, well, let me not start the example here, but well, I think you guys, I'm going to erase this. I think we all have you guys have the proof down now? I've been blathering on long enough that I think you probably caught up with me. All right. So example 1. And this will be a slightly symbolic example. So suppose you had vectors v1, v2, v3, and v4. And suppose that these are, in, let's say, R, 3. All right. And we could look at the reduced row echelon form of the matrix with these put together, like this, all right? And suppose that works out to be the following. Well, make it interesting here. 2, right? Now, you're like, okay, that's kind of weird. You didn't tell me what v1, v2, and v3, and v4 are, but you're telling me that the row reduction of the matrix, which is formed by putting them together, is that. Now I can ask you questions like, here's some questions. Question 1. Is v1, v2, v3 linearly independent? Question 2. Is v1, v2 linearly independent? Question 3. is V1, V3 linearly independent? Question 4 is, let's see here. Is V1, V4, well, let's say V1, V3, V4 linearly independent. So here's some questions I can ask. What does it mean for these sets to be linearly independent? I mean, our first definition was that there's no linear dependence amongst the vectors in a non-trivial sense, right? Another way is to phrase it, the sets are linearly independent provided that if we write down a linear combination of the vectors in the set equal to 0, it forces that to be the 0 combination. If we have that forced implication for any set of, any linear combination of vectors from the set, then that's going to be a linearly independent set. But certainly if we can exhibit a linear dependence of the vectors, then game over, it's not linearly independent. So how about my question 1? Can you answer it? What's our answer 1 here? Why? Now you just had since what? V2 equals to 2V1 by the what? By the column, by the column correspondence property applied to what? This V1, by the way, I'm just, in your test, I'm happy pretty much if you just say that much. But since we're learning, let me say a little bit more, just to be overly pedantic. We're applying the column correspondence property to V1, V3, 1, V2, V3, V4, and the row equivalent, what? RREF of that matrix. So even though I don't know the explicit matrix, V1, V2, V3, V4, it doesn't matter. I can still meaningfully answer questions about these unknown vectors. All right? But yes, that's a linear dependence, so it's not linearly independent, we find. I prefer you say something like, this is not quite optimal. I'd say no, V1, V2, V3 is not linearly independent, and then like that. What's past this line, I don't care if you usually say that. It's understood. Answer 2. Is V1, V2? Well, again, I think that's kind of a boring question. V1, V2 is linearly dependent since V2 is equal to 2 times V1 by the column correspondence property. Right. Now, look, is V1 equal to what? Is this V1? Is this V2? No, not necessarily. That is E1, and that is 2E2, right? Some system of unknown row operations reduces V1 and V2 to those. The point here, just to be clear, is that in fact this is E1 and this is 2E2, and it's just obvious that 2E1, it's obvious that 2E1 is twice E1, right? So that linear dependence is manifest in the reduced matrix. So by the column correspondence property, it must also be present in the currently arbitrary, unknown, except by labels, initial matrix. How about 3? Yes. V1, V3 is linearly independent since it's, the pivot columns. The pivot columns in, or man, I'm getting tired of writing this. I should have given this thing a name. It's about the 13th time I've written V1, V2, V3, V4 here. And the pivot columns in blah are linearly independent. Form a linearly independent set, to be more precise. Why do pivot columns form a linearly independent set? They're what? They're just E1, E2, .ek. In the help session yesterday, I proved that if you take a collection of standard basis vectors, they're linearly independent. It took us like 2 minutes. It's not a big deal. Do you see why linear independence is preserved? If we have a set of column vectors in a matrix A, and that set of column vectors is linearly independent, then the same set of column vectors, the corresponding set of column vectors in the row equivalent matrix, must also be linearly independent. That's essentially a corollary to the CCP, right? Because if we set, right, if you have the fact that C1, well, let me not even write it out. Let me just say it in words. If the linear combination of the original columns set equal to 0 implies that the coefficients are 0, right? Then that must imply that the linear combination of the same columns in the row equivalent matrix set equal to 0 also implies those same arbitrary coefficients are 0. So the column correspondence property also obviously transfers over linear independence of a subset of columns. This is a huge computational assist for these questions. Is V1, V3, V4 linearly independent? So let's say, and why not?
Because 3v1 plus 7v3
V4 by CCP. That is an abbreviation of a longer thought, which is the column correspondence property applied to the row equivalent matrices, the reduced row echelon form of V1, V2, V3, V4, and V1, V2, V3, V4. Right? Again, the linear dependence is manifest in the reduced row echelon form matrix, but it may be hidden in the initial matrix. It's certainly hidden in this initial matrix since I didn't even give you the numbers. Can't get more hidden than that. Yeah. Oh, to say a few things about spans. So let's see here. Let me just write a few things that are true about spans on the basis of what we have here. Like this. What can I, what positive thing can I say here? I could say this. I could say, hey, V2 is an element of the span of V1, right? V2 is an element of the span of V1. If V2 is twice V1, that means it's in the span of V1. Down here, among other things, one of the things I can glean from this linear dependence is that V4 is in the span of V1 and V3 because, again, what's the span? Something you need to memorize carefully for this course. It doesn't go away. You need to learn it. You need to understand it as deeply as you can. I'll write it down. Span of, let's say, V1, V2, well, let me be more careful. The span of a set S, right, is equal to C1, V1 plus plus CK, VK, such that K is a natural number, right? C1 through CK are in the field that we're looking at, and V1 through VK are in the set S. So in words, the span of S is the set of all possible finite linear combinations of vectors taken from S. Again, the span of S is the set of all finite linear combinations of vectors taken from S. This is span S. So, whether or not something's in the span, the question is, can you build that vector from a linear combination of the vectors in S? Right? One example I'll tell you guys, I said more, I would encourage you to watch the help session yesterday. I mean, there's a lot of good examples in there if you haven't seen them. So one of the things I got hurried at the end of the help session, I think it would help all of you if I went over it though. I sent you an announcement about this, but let me just work through a specific one of these examples in the low dimensional case. So I'm a little bit, this is not a direct continuation really of my current discussion. It's kind of more just me helping you with a difficult homework problem I've asked you, okay? But it's kind of an interesting problem though. So we've talked about, so span S, right? So the idea of the example is spans versus equations. All right, so in Calculus 3, if you've had that, we talk about, if you've got a plane, right? We talk about the equation of a plane. I gave you a homework problem already about this, right? And so a typical approach in Calc 3 is if you're given two vectors, like 1, 1, 1, and 0, 2, 3, or something like that. Then, in Calculus 3, what you do is you take the cross product of those two vectors, whatever that means, and that gives you the normal vector, and you just use the coefficients of this normal vector to write down the equation of the plane, right? So for us, we're looking at a homogeneous equation, so it's going to be a plane through the origin. Plane through the origin. But of course, if this thing is W, well, let's call it P. So P directly would just be the span of 1, 1, 1, 0, 2, 3. I mean, 0, 2, 3 and 1, 1, 1, these are serving the role of, these are tangent vectors to that plane. So the question I've asked you in a homework problem is essentially to rewrite that plane as an equation. And in fact, I've asked you a more general thing. I've given you two four-dimensional vectors, and I said find two equations in four unknowns which recovers that span of two four-dimensional vectors as an equation as well. So how would we, pick a point in here? Let's say x, y, z. I want x, y, z to be in the plane. What would that mean? Yeah, in the span, right? So, I mean, what does that mean? Yeah, it has to be a linear combination of those two vectors. So something like a times 1, 1, 1, right? Plus b times 0, 2, 3 equals to what? Well, equals to x, y, z. Now, to find the Cartesian equation, what do I need? I need an equation just involving x, y, z, right? I don't want a and b. And a and b are parameters. They're free to range over whatever. As they range over whatever, they trace out that whole plane. So if you look at this, this really gives me what? A, comma, a plus 2b, a plus 3b equal to x, y, z, right? Let me recast this as a matrix problem. This is really, you know, here I'll use A for this column, I'll use B for this column, and I'll use x, y, and z for this column, these columns. And I'll even put the zeros in there just for good measure. There's only three rows because there's only 3 equations here. The 3 equations come from the 3 components of this vector. First of all, A equals to x translates to what? I rewrite that as A minus x equals to 0, right? So that gives me the first row being 1, 0, minus 1, 0, 0. I rattled off some horrible 5-dimensional version of this at the end of the help session. I'm sorry about that. That probably was not helpful to you guys. I labor under the delusion that making things harder helps you guys sometimes. Let's see here, 0, minus 1, 0. That would be the second equation because A plus 2B minus y equals to 0. The third equation would be 1, 3, 0, 0, minus 1, right? Now row reduce this thing. What do you get? I guess you guys are going to make me do it, aren't you? All right, so row 2 minus row 1, row 3 minus row 1, what do we got? God. And then I guess I got to do row 3 minus 3 halves, row 2. When I subtract 3 halves, row 2, what happens? I get 0, I get 0, because that gives me a 3 minus 3. And so I get 1 minus 3 halves, which is what? Minus 1 half. And then what? 3 halves. Minus 1, I believe. That's not the reduced echelon form, but that's far enough I can see what I want. All right, we've got to go back to the interpretation here. This is the A, this is the B, this is the X, this is the Y, this is the Z, right? So what's this last row mean? This last row means that minus 1 half X plus 3 halves Y minus Z is equal to 0. That ought to be the equation of the plane we're looking for. What do the first 2 equations mean? The first equation, something like A is equal to X. The second equation is something like 2B is equal to minus X plus Y. Fantastic. I mean, X and Y are allowed to range over the plane, so that doesn't really tell you much. A and B are free variables. They can go over whatever real values you want. I mean, those are not what you're interested in. Those are true, but not interesting for our purposes here, which again, our goal, if you forgot what I said, is to find an equation for which the plane is the solution set. That equation, we just found it, is this right here. Let me clean that up. Multiply by 2, what do we got? Solution set of minus X plus 3y minus 2z equals to 0 if I haven't made some mistake. All right, moment of truth, quick check. This, by the geometry I shared with you guys in mission 1, I think, has normal what? Minus 1, 3, minus 2. For those of you who had calculus 3, I'm telling you old news. So notice that this vector should be perpendicular to both of these if my method was right. Well, clearly, this is perpendicular to that because 6 minus 6 is 0. This is perpendicular to 1, 1, 1 because minus 1 plus 3 minus 2 is 0. So yeah, we just found the normal without taking a cross product. Right? We found the normal by doing algebra. You mean, wait, we could have skipped the cross product in Calc 3? No, not really. It does other things. Yes. Anyway, this, if you can do this for 3-dimensional vectors, you can just as well do it for 4-dimensional vectors. For your 2 4-dimensional vectors, right, you think how this plays out. Instead of having 3 minus 1s, you'll have 4 minus 1s. And instead of just ignoring, I mean, you'll still ignore the top 2 rows because those will be the A and B quote-unquote rows, but the last 2 will both be significant equations. I mean, to pick out a 2-dimensional subset of 4 dimensions, you need 2 equations, 2 independent equations and 4 unknowns. If you'll allow me some counting that we haven't justified just yet in this course. That counting ultimately comes to us from the theory of dimensions, which we will prove. All right, let me move on. The other kind of hanging chad in this course, if you will, is solving many equations and many unknowns. So let me just tell you there's a lemma. If A if AY1 equals B1, AY2 equals to B2, AYK equals to BK, all right? So in other words, Y1, Y2, YK are solutions to, you know, AV1 equals to B1, AVK equals to BK, if you like to think about it that way. So I'm assuming what? I'm assuming that these K systems, there's a couple things there's 2 big things I'm assuming. The one big thing I'm assuming is that all of these systems have the same coefficient matrix. Right? Point number 1. They all share the same coefficient matrix. Number 2, they all have solutions. Right? So they're all consistent. So what would that say? Well, I haven't said, what's the punchline here? Then the reduced row echelon form of the superaugmented coefficient matrix, is the following. A, then you slap B1, B2, BK. So this is the so-called superaugmented coefficient matrix. Super just because it's got more than one, possibly. So we're getting greedy. Rather than just thinking about solving one system of equations, we're thinking about solving a whole bunch of them at once because they share the same coefficient matrix. Yes, we know this kind of problem comes up for the inverse problem, but you know what? It also comes up in applications where you have the same machine, which sets up sort of a matrix describing some physical process, and the different B's might be different data that the machine handles. So this kind of problem where you have the same coefficient matrix but different, different inhomogeneous terms, this also happens in applications. It's not just the inverse problem. Okay, anyway, so like that. Well, guess what this works out to? This works out to the reduced row echelon form of A, all right? And then Y1. Oh, shnikes. let me be greedier still. Well, trying to be not so special, but and A inverse exists, fine. Fine. Then that makes this I. And then what's that put over here? Precisely the solutions, y1, y2, yk. Does everyone have that? All right, let me make it worse. So we cross that out. Still assuming consistent. I wouldn't put y here. Let me put it down here. I would have the reduced to echelon form of A, and then I would have, let us say, I need some other letter. Pac-Man 1. Pac-Man 2. Pac-Man K. All right. Where the reduced row echelon form of the, for example, A with just Bj concatenated, just the regular augmented coefficient matrix is just what? So what I'm trying to say is you can read the solutions off the superaugmented coefficient matrix in the same way you can read them off a regular augmented matrix. That's what I'm trying to say here. I'm having trouble. Let me, with an example. So, actually. Well, anyway, does anyone actually have trouble? Has everyone read the notes about this? Do you have understanding what I'm talking about? I have a specific example in the notes where I solve two 3x3 problems separately. Then what I do is I take those two 3x3 problems and I put them together into a superaugmented matrix. I row reduce it, and I show you that the superaugmented matrix contains the solutions to both problems just solved with separate. So that's in the notes. Read that if you would. I shouldn't spend more time. I don't think I'm really adding much to your understanding by continuing to try to find. I'll be writing ghosts and SpongeBobs before we know it. We should stop here. Anyway, this is precisely what drives the inverse finding algorithm, right? Yep.
You crossed out and A inverse exists. Does that imply that A inverse does not exist, or we don't know if A inverse exists?
Oh, I'm saying that A might not even be square. So I'm not saying anything particularly malevolent about A. I mean, it could be something like that the reduced row echelon form of A with, B1, B2, B3 is equal to, I don't know, 1, 2, 0, 1, 0, 0, like that. Keep it simple. And then 3, 7, 0, 1, 9, pi. I didn't see that coming, did you? And so what I could tell from that, well, first of all, A would be 2 by 3, right? And so if I was to try to solve the problem AV equal to B1, I can solve AV equal to B1 by looking at this, because that corresponds to the B1, right? So what's that? What do I learn here? I learned that x plus 2y equals to 3, and I learned that z is equal to 7 for that B1 solution. So my v has the form xyz equal to what? Well, 3 minus 2y, comma y, comma 7 for any y in the field. I'll say reals since I put pi in there. Why not? In contrast, if I was to solve AV equal to B2, what would I have? AV equals to B2. See, then I would look at I would say, aha, well, this tracks over to here by the mechanics of row reduction. And so that's going to tell me that x plus 2y equals to 0 for my v. And I got z equal to 1, yeah? So v for the second system is going to be given by minus 2y, y 1 for any y in the reals. The point is, I can solve 3 separate systems of 2 equations and 3 unknowns with 1 row reduction using this method. And this is what we do to find the inverse matrix. Because to find the inverse matrix is to solve what? We're trying to find solutions to, I see some of you looking still uncertain. So I'll write it out again. So what is it? How do we find A inverse? How do we do that? So we're trying to solve A inverse equal to the identity matrix, right? So what is that? If we say A inverse is y1, y2, yn, so these are unknown columns, right? We want to find those. What does that amount to? That's A times, y1 through yn, which by the column-by-column multiplication is ay1, ay2, ayn equal to I. What is I, though? That's e1, e2, en. So to find the inverse of a matrix is to solve n systems of n unknowns simultaneously, all sharing the same coefficient matrix. So we have to solve ay1 equal to e1, ay2 equal to e2, and so forth, right? How do you do that? The best way to do it is to solve the superaugmented coefficient matrix corresponding to this system of systems, right? So rather than solving these separately, one at a time, you take it all, you chunk it into one big old problem, and you figure out what's the reduced or echelon form of A concatenated with E1, E2, en. Of course, this is exactly the identity matrix, right? And by the way, the thing I was limiting myself to assuming invertibility and then assuming consistency, mostly because I don't want to get all complicated in my statement. But really, this superaugmented thing still makes sense when you have inconsistent problems. It just gets kind of messy what happens with the different inconsistent problems. I have a simple example to show you what I'm talking about. If A inverse exists, so we know what happens here. This becomes the identity. And then what's over here? The solutions, right? y1, yn, which we know is A inverse. So that's why we do this. Why we reduce A with the identity put next to it. That's our way of solving all those equations at once. I was going to spend 10 minutes on the determinant today. Oh well. One last comment. So if we had, if you have the matrix 1, 0, 1, 0, and 1, 0, 0, 0. So suppose that's A. And if we have B1 equal to 0, 1, 0, 0, if we have B2 equal to 0, 0, 0, 1, it's not, you should be able to convince yourself that AV1 equals to B1, no solution. And you should also be able to convince yourself that AV2 equal to B2 has no solution. Can you tell me why? What is A times V1? What is A times V2 in terms of column multiplication? I mean, in terms of the sum of columns. What have we said about matrix column multiplication? Matrix column multiplication is a linear combination of the columns, right? Is there any way you can build B1, which is E2, from a linear combination of these two? No way you can do it. There's zeros in the second spot. You can't create a non-zero thing from 0 like that. You can't do it. How about B2 is E4? You cannot create a non-zero fourth entry from these two column vectors, right? So these two systems have no solution. And on the other hand, are these linearly independent? Yes. So what happens with the reducer echelon form? You get 1, 1, 1. And the second one is also 1, 1, 1, with zeros in the bottom. Right? So they have the same reduced row echelon form, both of these inconsistent systems. When you look at the superaugmented coefficient matrix, what happens? You get this. So this is the wrinkle that has, that's why I assumed invertible or consistent, is because it's kind of hard to explain how the ones get wrinkled on the end of the list, because, you know, the first inconsistent system makes the first one below the reducer echelon form of A past the double bar in the superaugmentation, and the next inconsistent system will either follow that inconsistent one, or if it's a genuinely new inconsistent thing, it'll add a new pivot past the double augmentation bar. Anyway, it's complicated to explain, but it's my best example to give it to you without spending a half-hour class on a relatively technical and uninteresting point. Have a great weekend. Oh, and don't forget the opening ceremonies for the Olympics, short hours away on NBC. No? You're not? You guys look, go Team USA. Go USA. 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 No? All right.